ladies and gentlemen. In that, ladies and gentlemen, I include all the students and a particular welcome to the Expats Club from Patio. It's very pleased to see so many people here today. It is indeed a pleasure to welcome you all here to Asian University today. In particular, I would like to extend a very warm welcome to our special guest, Nobel laureate, Professor Riccardo Giacconi. At Asian University, we're proud to be part of this Bridges event. Bridges event sponsored and supported by the International Peace Foundation. It is to promote the Kingdom of Thailand as a centre for dialogue and international understanding. The Master of Ceremonies today is Ms. Natamon. Ms. Natamon is a third-year student in the Faculty of Liberal Arts. She's possibly better known to many of you as she appears frequently on television. In handing over the ceremonies to Ms. Natamon, I'd once again like to warmly welcome you all to this special event. And may I ask if you could kindly check your mobile phones to ensure that they're turned off and do not disturb the event. Thank you very much.
Thank you, Dr. Neil. Ladies and gentlemen, it is my pleasure to act as Master of Ceremonies for today's special event. Before Professor Giacconi delivers his lecture, I would like to introduce him to you briefly. Professor Giacconi was born in Genoa, Italy, 1931, but spent most of his life until 1956 in Milan. He received his doctorate from the University of Milan in 1954. I noted from his autobiography that he was often a discipline problem at school, so there's still some hope for some of us. In 1956, he was awarded a Fulbright scholarship, which led to him moving to the United States. In the following years, Professor Giacconi took on many academic and professional challenges and worked in leading positions at American Science and Engineering Incorporated, as a professor for astronomy at Harvard University, and as a director for the Space Telescope Science Institute. At this institute, he was planning and executing the science operations of the Hubble Space Telescope. In the 1990s, he was a professor at the University of Milan and Director General of the European Southern Observatory. Professor Giacconi detected for the first time a source of X-rays outside our solar system, and also sources of X-rays that are now considered to contain black holes. His contributions helped lay the foundations of X-ray astronomy and provided us a new challenge that has changed the way we look at our universe. On December the 10th, 2002, Professor Giacconi was awarded the Nobel Prize for Physics.
So, ladies and gentlemen, dear colleagues, students, I will start with a little introduction so that you can forgive me if I talk about things that you may not be interested in. I prepared 3 lectures in coming to Thailand, and I delivered all 3 of them in one forum or another. The first one, which is the one I will again do today, had the purpose of acquainting those of you who are interested in astronomy in some of the latest point of view in astronomical research. The second one had to do with the relationship between basic and applied research. I have been involved in both. I strongly believe that there isn't that much difference anymore, and given the fact that the time between basic research findings and application is becoming increasingly shorter, that it's almost difficult to distinguish whether someone is working on The third point was management of large projects, which I was asked to do on behalf of some of the various entities which are working in Thailand. And today, I would just go back to the beginning, namely, why is it that it's so nice to do science, and why scientists enjoy doing what they're doing. I thought I would, before I go into X-ray astronomy is a little daunting, and people tend to think, why do we need to do something this far away, abstruse, and so forth. And so I'll try to introduce it by saying the obvious for those of you who are experienced in astronomy, and just furnishing a little background for those who do not know astronomy at all. So let's start from the sun, a normal cool star. Thank God, because if it emitted in X-rays, it would fry us pretty much. And the fact that our evolution on Earth has emphasized the fact that we can see in light, which has a wavelength that the sun emits, and can come down through our atmosphere. Now, is that a fair representation of the universe as it is? The answer is not at all. And however, in order to find out how the universe actually, what is going on, we had to wait until after World War II, when rockets and satellites that could carry out observations above the Earth's atmosphere were made available by technology. And what we find is what perhaps one would have expected, but wasn't really foreseen, which is the following. If you think about physical processes which occur even in the laboratory, you find out that different types of radiation are emitted by different physical processes or different objects at different temperatures. For instance, our own sun is a temperature of about 6,000 degrees, so it emits mostly in the infrared and in the visible. There are stars which have temperatures of 50,000 degrees, and those mostly emit in the ultraviolet. And finally, there are systems which are at very high temperature, millions of degrees, and they emit in X-rays. So in order to study the universe as it is, the distribution of mass, how structures are formed from the initial explosion to today, we have to study the universe in many different wavelength bands, and in particular, the space, the ability to work in space has made available the ultraviolet and the X-rays. World War II also developed radio astronomy, which allowed the discovery of a number of other objects which are emitting mostly in radio waves. Now again, to make it very short, but to give you some idea of the names and what I'm going to say later on, a normal star is formed early after the Big Bang, and it can only be formed on those elements which are around, which are very light elements, hydrogen, helium, beryllium. It cooks these elements inside itself through thermonuclear fusion, and it makes heavier elements, carbon, up to iron. It then exhausts all the fuel it has, and so it collapses and creates an explosion whereby all of these elements are diffused in interstellar space. From these elements, then a second generation of stars can form, for which the sun could be an example, which contain both heavy and light elements. Planets can form, also containing both heavy and light elements. And so, for instance, you can develop, and by you I mean people, hydrogen contained in the water in your body comes directly from the Big Bang, the initial explosion. Didn't need any manufacturing. But the iron that makes the hemoglobin in your blood and all the rest of the elements that you have in you come from supernova explosions, from the burst of a star and then the rebirth through this mixing together and forming of new generations of stars. So, without knowing all of this wonderful philosophical background, I was a young student who had come, I was already teaching to university. I had a teacher who was Beppo Chialini, who had actually worked with Professor Blackett at Imperial University. And he had become fascinated. He had left Italy because of the fascist regime and had lived abroad. He was working with Professor Blackett at Imperial College when Blackett obtained the Nobel Prize in physics for discovering positrons. And he was fascinated with the United States and told me, go west, young man. And I went west and, on a Fulbright fellowship and never went back except to direct some European enterprises. I had done my work in cosmic ray particles, elementary particles, a field that was changing very rapidly from studying natural elementary particles and coming from the cosmic rays to accelerators. And I didn't like big research. I was very scared about big research. I thought that one would lose one's individuality in it. And so I was looking for something to do. I joined a private corporation whose purpose was to work for the government in areas like education, medicine, defense. And I was given the job to start space science in this corporation. I was 28 years old, the corporation was 28 people. So it was a very nice nurturing ground for people with initiative. And this was the era when we could do everything. So there was a really fantastic drive. And I was, a suggestion was made to me, think about X-ray astronomy. So at the time, so I'll start now getting into the subject, and I'll just say the following. X-rays have been observed from the sun for 10 years before 1959, which is when I started really getting involved. And the number of X-rays that come out from the sun is very small because the sun is a cool star. And if, in fact, all stars were like the sun, it would have taken an improvement in our capability to detect X-rays in space of a factor of 10 million. We see a big step. In fact, when I went to propose to NASA that I should look for X-ray stars, I said, there are no X-ray stars, go away. And so I started thinking about this quite a bit and tried to figure out whether there could be objects which were emitting a lot of X-rays. That was fairly unknown. However, I found in a certain way that all my preparation up to that had prepared me precisely for this job, meaning to take the experiments which had been done up to that and really make them much more sensitive in two ways. One, by creating X-ray optics, whereby I could use the same kind of advantage that you have in visible light. You gather light from a large telescope onto a small CCD camera so that you have a tremendous scale. You see that very short. And the other one was just improving the equipment that was available there, which basically was Geiger counters. Geiger counters are cylinders filled with gas. A particle comes through that. Few electrons are formed. There is a difference of potential between the central wire and the walls, and these pulses multiply and you get something that you observe electrically. And this has been used because of rays. If you wanted to detect X-rays, you made a window, you put a piece of marble on it to let them through, and that's how, fairly primitive, but that's how we were counting X-rays at the time. So, let me just now go through, and I will not describe this table in any at all, except to say that it showed that you did need to modify the instruments to find anything at all. This was the first payload that we set up. It was changed with respect to others in the sense that we recognized that we didn't know where to expect X-ray sources within a huge field of view. So anywhere in the sky. Am I doing? Yes, I think I'm doing something, but I don't know what. Electrical discharge, maybe. I was rubbing my, sorry. It's called that some do it. Anyway, so that was one point, make a large field of view. The second one was because I knew about cosmic rays, there were as many cosmic rays per unit area as you would expect X-rays. So clearly, having a way of throwing them out was a good idea because you would decrease the background. And the third thing was to have a much larger area, as large as we could make it. So we made these two detectors, and we had several, so that we put them on a rocket. The rocket goes up about the atmosphere, so it has to go up about 100 kilometers. And then for the 5 minutes that it stays about 100 kilometers, you scan the sky and try to find if you have a source. And lo and behold, after 3 failures, one the rocket blew up, the other one the doors didn't open, and so forth. Finally, in '62, we had a flight where we observed this very very strong signal here. Now, what is plotted here is azimuth, that is the points of complex here. And this is number of counts, and we sum all the counts we had received. And the thing that we found, basically, was two things. One, a kind of a flat background of radiation from all over the sky, and then this big peak. And in the direction in which we found this big peak, there was no strong optical source. This particular finding, rough as it was, gave us a tremendous impetus to ourselves and other groups to join in the search for X-ray sources. Because such an object, there was no theory that predicted that such an object would exist. An object in which 99.9% of the radiation was emitted in X-rays. If you have an X-ray source on the ground now, as you go to the dentist, you see that there are tremendous coils to cool down the target because most of what you produce is heat, and only a very minute amount comes out in X-rays. So this was a very strange celestial object with a very strange process going on. And immediately once you say that, here is the discovery, the potential for discoveries. Scientists are very egotistical people. They want to spend little effort to obtain large results because they only have one lifetime in which to do it. And so they are looking for high-level situation. This obviously was a very high-level situation. So I won't go through, let me see. I won't go through the various years. It's about 10 years from that finding to when we flew this little satellite. Interestingly enough, this was also done within the private corporation at a fixed price of $5 million at the time. It was launched in 1970. I'm emphasizing the private corporation to say that part of my belief and part of what I observed is not all fundamental research is done in university or in non-for-profit organization. A lot is done in pieces of profit organizations. Bell Labs is a clear example. So there was this little satellite about the size, my size. It has two fields of view, 5 by 5 degrees, 1/2 by 5. We scan the sky, and in different crossings we can determine position. And here is in galactic coordinate, meaning this is plotted with 0 being the plane of our Milky Way. And so these are all stars in our galaxy. And above that, at high galactic latitude, there are extragalactic sources. This finding by itself, there were about 300 sources. They represented different kinds of objects. Let me just stop a moment on this one because I won't discuss this anymore. Coma. Coma is an ensemble of galaxies. Just like stars don't like to live alone, they live in galaxies. Galaxies don't like to live alone, they live in groups of galaxies. And these are the largest mass conglomerate in the universe. Now, in this particular, what is it that emits this X-rays from this particular galaxy, group of galaxies? It turns out it's not the galaxies themselves, it's not the stars, it is gas at very, very high temperature, millions of degrees or more, which pervades the space between the galaxies. And although very thin and tenuous and never observed in visible light or any other means, it contains 5 times more mass than all the galaxies and all the stars put together. Thus, the statement that most of the mass that in barrier that is contained in our universe is in fact in a form which we cannot see using our eyes or looking in visible light. The other thing that I wanted to say is here is the galactic plane, many stars. The size of the dots has to do with how bright they were by convention. This was the first one we ever detected. And I will try to now say what it is that we were seeing in the first rocket flight. What was this object that we were looking at? Now, using this, I'll jump back. Using this satellite, this new satellite, we have a tremendous advantage with respect to having rockets, because instead of staying up 5 minutes, we could stay up for years. So we can do a number of experiments, and here you see now the same source that we had seen in the first, when we first discovered it, but now look how much better, cleaner it is, and here time is in seconds, and what you are seeing distributed over these angles has to do with the fact that the satellite is rotating on itself, and you see different sources at different times. We could also change the speed of rotation of this satellite and make it go either very, very slow, 2 degrees per second was the typical thing, but it could go 10 times slower or a little bit faster. When we did go slower, it meant that we stayed on a particular object for a long time, because it would take a long time to cross the field of view. And so this triangular shape you see here spread out somehow and expanded. Now, when we were looking at an object such as that, in particular that Sectorus X3, here is the envelope, triangular envelope that I was mentioning. But then all of these pulsations had nothing to do with triangle with the instrument. It had to do with what the star itself was doing, or the stellar system was doing. What you are seeing here, just to give you an idea of how different it is from the behavior of our own sun, here there is this object which is changing intensities by factors maybe 10 in times of order of seconds. It's just as if the sun was going on and off within a second or two. Now, what is this object? In radio astronomy, Lewis had discovered pulsars. These were stars at the end of their evolution, which had collapsed because there was no way that the interior fire could keep up the radius of this sphere. And a star of a mass about the mass of the sun would collapse in about 10 kilometers. It was a very strong magnetic field. It would rotate on itself and produce jet of particles, which then were observed in radio waves. So we asked ourselves, is that what we were observing, a pulsar? And it turned out that no, that was not quite what we were observing. As we tried to measure the pulsation, and here look at the time, it's in days. See? So here is the star, this stellar object which is bright, and here is dim, and then bright again. And the period of pulsation is changing according to a sinusoid, which is the signature of a Doppler effect of a source in orbit in another star. I hope most of you know a Doppler effect, the train coming towards you, right, the pitch going higher, the train going away, the pitch going lower. We are seeing this in X-rays, and the precision of the measurement is such that, in fact, you can't see the error bars on that. So the solution is obvious, right? Here is the point where the star, the X-ray emitting object is further from us, hidden by the companion star. Here's where it's right in front of us, and this is why the null points of the velocity, if you wish, are coming. And so the model has become very simple. It is this X-ray pulsating source going around the normal star. Here is the eclipse, here's the observer, and everything is okay. The point is no, everything is not okay. And this is where we come to a slightly more interesting part, which is the following. We measure, again, remember, we are now, the satellite was launched in 71, we went on 72, 73, and then there was a British satellite called Ariel 5 that was flown here, and we measure this period of pulsation. And what we observe is that instead of losing energy, as a pulsar would do, because it's transferring its rotational energy in emitting all of this radiation, this particular star is actually speeding up. And so therefore, it's actually gaining energy, not losing it. So here is a process which is very different then from what we knew before. And the explanation here, what this shows is a cut in the gravitational potential, if you wish, of this object. And imagine having the normal star represented by a vessel containing gas or water, and it falls down a deep well, so deep, because the star is so compact, that a proton will acquire 100 times more energy through this process than it would acquire through nuclear burning. So this is one of the most powerful sources of energy that nature has figured out how to produce, and it explains not only this particular object, stellar object, but also the emission from the very bright galaxies which contain inside themselves supermassive black holes. And the first black hole was the one that we saw. This was an example of the object, a gas falling on a neutron star, and then I jumped away. But here is another one which we observed with the same satellite, in which there is a normal star falling onto something from which light cannot escape. That was the definition of black hole. We first saw this in of a stellar, for a black hole of a stellar mass. We now know that this system, that is to have a galaxy with a black hole in the center and emitting the tremendous amount of radiation, is the normal way in which an active galaxy is behaving. Now, I want to now turn, so we solved the first problem. What was that very strange source? It's a source which is made of a binary system, a star which has collapsed either into a neutron star or a black hole, and a normal star companion that furnishes the fuel, so to speak. And essentially most of the sources that we know are of that type. But what about this background that we were seeing? Well, that required 40 years. We just was solved that after the launch of a satellite called Chandra, short for Chandrasekhar, which was launched by NASA in 2002, actually. 2001, sorry. What is shown here is a mirror for X-rays, which actually also was developed very early on at American Science and Engineering, it is still a corporation, and where with two reflections you can obtain an image in X-rays from a very far away source. Now, the reason why you have to have this very strange configuration is because if you went head-on into a wall with X-rays, they would just be absorbed. So it's only if you scatter them at very grazing incidence that you actually have very high efficiency of reflection. I won't bother you too much with the development of this, just to say, if you take a picture of the sun in X-rays by means of this telescope, you see something which is completely different. It's true, as I said, that from the sun, very few X-rays come, but those that come from very hot gas, plasma, hot plasma, such as you would observe if we ever obtain a fusion reactor. Okay? So I'm trying to imply that there are consequences for diagnostic of fusion in fusion research. But anyway, this hot plasma, which is contained in the sun's magnetic field. Several generations of satellite, I'm jumping fast, thank God I have a fast computer here. And finally we get to the one which is being launched in 2001. Now this particular telescope is not a man-sized small thing. It's something that costs 1.7 billion. It is about the size of a largest truck. It weighed several tons, was put up by the shuttle and then launched into higher orbit by auxiliary engines. And it has dominated X-ray astronomy, practically speaking, since it went up. It contains a telescope with the general shape that I told you before, except it has 4 different surfaces to obtain more area. Now this thing has taken pictures of lots of objects. These are pulsars. This is an X-ray picture. This is a picture from a Hubble Space Telescope. And the exposures were taken on different occasions. So this is not going as fast as you see. It may be taken 2 years for the collection of these different photographs. But you can see now directly, both in X-rays and in visible light, one of these pulsars that I was describing earlier on, with an angular resolution which is identical in visible light and the best that can be done. The best can be done in visible light and what can be done in X-rays. Now the intensity that we can observe is 1 billion times smaller than the first detector that we launched. So we had 1 billion times means the difference between the naked eye and the largest telescope ever built on Earth, Kent, for instance, or the very large telescope. So the technological development has been very great. Okay, this is a different picture. Is the center of a galaxy now, not anymore a star, but there is one of the supermassive black holes. And here's the last experiment, which I carried out anyway in the last 2-3 years, in which I take a picture of the sky where no particular thing is supposed to be going on. And the size of this is about, the moon will look about this big. And within this very small region of the sky, we see something like 360 different sources. They are very far away. Each one of them contains a black hole, actually. Or most of them, 90% of them contain black holes. And they are very, very distant. And the reason why we were seeing a uniform background was because we didn't have the visual acuity or the resolution to distinguish one little source from the other, so they look like a blurred fog. But what this is the very, very early galaxies. This again, I won't go through that. I'll jump that. And this is how we find out how far the sources are. These are the X-ray positions, these X-ray density contours, and inside superimposed on the Hubble Space Telescope image, and then we try to find the spectrum, which gives us a measurement of the distance and these are so faint that we are seeing sources that the largest optical telescopes cannot see. We try to find them in other wavelengths. Again, let me go fast. Here, for instance, is an attempt to see this X-ray source described by these contours with a Hubble Space Telescope. We see nothing, but we now go to the most recent addition that we have had on our observatory fleet, if you wish, Spitzer spacecraft, which sees in the infrared and sees through the dust, which hides the visible light, but lets through infrared and X-ray. I won't go through that, won't go through that, or this. And here is one of the things that is also interesting, and that allows me to make a couple of summary remarks. Here is this picture is the sum of, I think, 8 exposures, which were taken in time at the time shown by this arrow. So you see that it starts here, then it jumps there, then etc. If you look at these sources, let me see, oh, okay, look at this one. You see that it's coming and going, and so it means that this whole object, which is at a distance maybe 90% the life of the universe, is pulsating with, or changing its intensity in a drastic manner in times of the order of a year. So a light year is something that's a small region within a galaxy. And this is because the central energy engine is this very small body, which is a supermassive black hole. Now, the point I wanted to derive from this is I tried to show you and to tell you that your iron comes from supernova explosion. The origin of the universe is an enormous explosion. If you look at the sky in X-ray, you reveal a number of phenomena which are taking place very, very fast. So our view of the sky represented, I don't know, if you had seen Space Odyssey 2000 or something, there is this big space station that goes around with the sedate Strauss waltz. And then you can imagine of galaxies which are very slowly evolving because they are burning their nuclear fuel over billions of years, etc. But those are not the important and most energetic events of the universe. That's not where most of the mass is, and that's not where the production and the fusion of elements is taking place. So high energy astronomy, we're extremely lucky that high energy astronomy had a profound significance with respect to the creation, the development, and the evolution of structure in the universe. I think I have one more, which I think is dutiful to do. I have, talked about all of this as an actor in the play, about the things that I have been most interested in myself. This is a compendium of each dot represents a satellite launch. And here is time, and here is how sensitive they were, and of course, here is the Discovery rocket, and then we keep going until now we are here with AXA, which is now has the name Chandra, and XMM, which is called Newton. This is an American enterprise, this is a European enterprise, and as you see, the flux that could be observed has become fainter and fainter, and so we could see many different phenomena, X-ray stars, supernova, binaries, clusters, active galactic nuclei. They're sequenced stars, and they start just like the sun can now be seen. Normal galaxy, distant cluster, protogalaxies, etc. The point of showing this stuff was not to say so only that X-ray astronomy has been progressing very fast, but that it has done so through a number of collaborations. SpectrumX is Russian, Astro D is Japanese, Ginga, Tema, Kucho are Japanese, ExoSat is European, and so forth. So the groups are involved in X-ray astronomy in the entire world, and the reason we have made so much progress is because we have worked very closely and very cooperatively with each other. Thank you.
Thank you, Professor Giacconi. And now is the time to open this presentation to any questions.
Yes. I don't know about the situation in the UK. I can tell you that in the United States, we have had a golden period in which Hubble Space Telescope, Chandra, Gamma Ray telescopes have been set up. And now we are at a crucial period where we would like to extend astronomy observations to other things, for instance, to gravitational waves, if any exist, discovering or finding gravitational waves. We also would like to keep searching for new planets, as has been done very profitably, about 100 new planets around other stellar systems that we discovered the last few years. Now, all of this is coming to a jam of requests, which much exceed the budget that we have in the United States. We are trying very hard to do work cooperatively now, saying that well, in the United States you need cooperation at the national level when even Harvard doesn't have enough money to give you to do your research, or Caltech, or donors. So those are the national observatories, which are forced by the cost. I think now the costs are getting so high that the only way to do this thing is by international, intercontinental, if you wish, cooperation. At the moment, for instance, there is a program. So what have the UK, if you're particularly interested in the UK, done? They have chosen to spend less money at home and join an international organization, which is ESO. That immediately gives them access to the largest telescope system on Earth. They are also participating in a new enterprise, which is a joint European, US and Canada and Japan enterprise, a third of $1 billion for radio astronomy observatory, which is being built in Chile. So I think we are going more and more toward this kind of international cooperative things, which are very difficult to manage, we are finding, but which become a necessity. And I think that England will do very well as part of this international organization, but couldn't be competitive on a national basis. It's a long answer, but I thought it might be useful. Sorry, I will promise to respond faster.
Previous question in a way, and that is, you spoke of a private firm, and I wondered if that private firm ever got money other than from government, in other words, or other than said donations. Were they producing your work, produce something that industry was having to pay for?
Yeah. Well, the first thing that came out from the ability to detect very low fluxes of X-rays was the kind of thing that you go where you put your suitcase in airports and where it does X-ray scanning. That was the product of this firm. The other one was this X-ray telescope, which of course can be used as a diagnostic tool for energy development. Now, interestingly enough, this firm, including me, I was a partner the same name as the firm that really started that. But there was an immediate fallout of progress. The most important, I think, result from this research that you may be familiar with was one that we actually missed. That is this very effective X-ray scanning technique, which is different from normal X-ray picture. Normal X-ray picture, you have a source back there and a plate, and they put you there, and okay. That's not an effective way to get an X-ray picture. The most effective way is to have a detector, to have a scanning X-ray beam that scans you or whatever. It turns out you can then take pictures of X-ray pictures of people with 1 million times less dose that you would in a normal X-ray picture. This, for instance, the first application was you could do X-rays of pregnant women without affecting anything. The second application was to go a little beyond. Instead of having just one beam, you would have many, and you would rotate them, and you would then solve the fairly complex system of differential equations to reconstruct the image. Now, we have gotten to the point of thinking of the many, rotating them, and we have not solved the differential equation. So somebody else got the Nobel Prize for what then became the CAT scanner. But all I'm trying to say is that these were developments which were occurring in industry, which had a lot of application, and I think CAT scanner is one of the main powerful tools, for instance, for tumor research and so forth. I mean, so, yes, that's why I was saying that in my mind I didn't see any difference between applied and basic research. We had to stay alive. We didn't make much money. To give you an example, when I had this fixed price contract to build this satellite, this was, ridiculous from a university point of view. I then ran out of money, and I still wanted to do some little thing with my detector. So I went to the board of directors, and I told them that this was very important for the future of the corporation, et cetera, et cetera. They actually believed me, and they gave me $100,000 of profit funds, which was truly remarkable. Those were very hard to come by. And in fact, then they had a lot of contracts from the government, which had to do with defense, which had to do with fusion, etc., and the machines which I just described. It's, I think that what brought this about was the fact that we had a very easy exchange with academia and industry. I mean, people did not feel that working for industry was beneath their dignity. Many of the people, in fact, most of the people in my group were failures at MIT or Harvard, who then redeemed themselves working like mad. And many were somewhat strange, like me. I could never have made a normal academic career. I just became a Harvard professor. I mean, from executive vice president of a corporation, I went to Harvard, and then I left Harvard, which also is unusual. I mean, I left on my own volition. I wasn't kicked out. And I went to direct the Space Telescope Science Institute, which I found very interesting, and so on. So this is not unique to me. I mean, I don't know, the president of Genome Corporation tried to create 6 corporations, failed 5 times, now it's okay. The discovery of the laser, the discovery of semiconductors, and so on. Those were all at the edge between basic research, fundamental new physics was being used, and application. And the people who do the basic research are not stupid. I mean, so they understand the potential application. It's just they don't know how to do it. And university here play a major role now in the United States in trying to help these people realize they transfer the science into technology and realize royalties which are of benefit to the university, so that the endowment at Harvard is getting some royalties out of the discoveries in biochemistry and so forth. Okay, so that's why I spent the time to discuss this point. Yes?
You said that when you want to contact yourself to extra astronaut, you're afraid that you will lose the freedom. So how do you plan to...
I will lose what? Well, I tell you, there is a difference between being the boss of 500 people and being one of the 500 people. And I found that I didn't have any problem running 500 or more people as far as my individuality, and I tried very hard to make them participate in all the decision-making, discussions of budget, promotions and advancements, and so forth. So that, let me, do I have 5 minutes? Okay. Technical enterprises which have high content cannot be done by top-down direction. It doesn't work. It works by top-down inspiration, vision, communication. But basically, the technical people who are involved must make the program their own. If you succeed in doing that, then everybody experiences professional and personal growth as it's part of this enterprise, and they are not losing their individuality, they are acquiring experience, and then being able to go on their own. I've tried very, very hard to do that, and apparently it's worked out, let me put it that way. You look skeptical. Okay, there are many means you do that. I mean, it's, and I can't go into a whole management course here. Yes.
Back to the management themselves. What is the practical value, or is there a practical value to us to research that you've done with the telescope, particularly the X-ray?
Well, the technology we had to develop certainly has found, at least in health and in defense and in energy development and so forth. So I think we earn our keep. Now beyond that, I think that what I've been telling you is that looking at the world in visible light is a very provincial way to look at the world, which is created and constituted not for our benefit at all, but according to physical laws which are intrinsic in nature. And I would hope that this gives two messages. One is that it's very interesting to find out these physical laws so that we understand, because even things we do not know or understand can kill us. But the other one, to give a certain feeling of humbleness that there is a universe out there that little cares what happens to us. Okay? So, it's, the meaning of it all, I think, is in the communication we can have among ourselves as human beings. Because the universe itself has no particular preference for having a star that burns you off and one that nurtures life as we know it. Okay. So it's cultural. What I try to tell you is that I think that the main value, in my mind anyway, of this work is cultural. We have learned, we have built on the back of a lot of people, great scientists that came before us, and we have gone way beyond that. And we are still going. We have learned we know nothing about what makes the universe tick. I mean, 70% of the matter in the universe, we don't know what it is. The 30% that we think we know what it is, we don't know what kind of particle makes it up, and we only recognize a few percent. Those we know. So it's, if you don't find this interesting, well then I don't know what to say to you. Sorry about that. Okay. Yes.
Hello. Thank you very much for coming and sharing with us the keynote of the guide. I have a couple of
I think that where the stuff came from in the Big Bang theory is a question of theology rather than science, because we have no information through the Big Bang. And therefore that you can assume whatever you want. From a theoretical point of view, you can construct theories whereby the Big Bang itself is due to a quantum fluctuation in the vacuum field. I mean, I'm now telling you the words, but I don't expect you to. And this would be one of the many universes which has been built. And then there is a big debate on how come this universe is friendly to us, so to speak. And another point of view is, well, the universe is friendly to us because if it wasn't friendly, we wouldn't be here to see it. And therefore we are big, okay? So that's one. The other one, as to the shrinking rate of the sun, that assumes that the sun and the earth were always in stable orbits around each other, which is not at all clear. But I think that the reason why we have believed that we understand how the sun is going to work and evolve is because we are looking at this forest, so to speak, meaning many, many stars. And some are young, like it would be in a forest, some are seedlings, some are old trees. And so we can extrapolate between one and the other to try to figure out to make a life history between all of them. The sun will ultimately burn out, and by that time I hope we have the technical means to emigrate to some other shore. I mean, it's okay, but that's it. Yes.
Since your work is based upon the light radiation, far distant locations, and the sun is so close to us,
Yes.
is there a potential that we could look to the sun for a cleaner energy source than, say, hydrocarbons and so forth that you're burning today? Is it within our technology if we were to apply ourselves to this? Is there enough energy coming from the sun to meet our needs?
The second part of your question did not have to do with the first, so let me try to respond to the first. The sun works by fusion, nuclear fusion, not nuclear fission, but fusion. And one potential powerful source of energy is the fusion of hydrogen into higher number elements, which is being tried now since 1958. I mean, there have been different experiments in the United States, in France, in Germany, in Russia, and so on. There is now a program called ITER, I-T-E-R, which is a international program to build the first fusion reactor, or to advance further our knowledge. I mean, we don't know whether they're going to be successful. And it's supported by these large groups. The reason why I was saying that sometimes the management becomes difficult is that there were two proposals, one from Japan and one from France, to house this laboratory. The Japanese proposed Japan, and they were supported by the United States. The French proposed France, and they were supported by Russia. At the moment, it might be that there will be two programs or something. But that would be the expectation and hope that fusion will be the source for energy. Now, the last part of your question was, can we utilize solar energy, so to speak, to do something? And of course, you can utilize solar energy by, I mean, after all, we are utilizing stored solar energy when we get petroleum from the ground, right? Because these are forests which grew in the past and then decayed and so forth. We can grow our own forest or sugar cane and make fuels out of it. I personally doubt that this is going to be the way of the future. It's just too cumbersome. I mean, too much effort. I mean, you would have to create enormous plantations of stuff that then you chew up to make gasoline. So my own opinion is that fusion is the way of the future. It's clean, it doesn't pollute, it doesn't give you radioactive wastes, so it will be the right way. Okay.
Any more questions?
Okay. Thank you.
There's one. There's
Oh,
one.
there is? I love it. You're a repeater, are you not? I see.
Professor, you said that black holes emit huge amounts of energy.
Yes.
Sometime in the future, do you think it's a possibility that we'll be able to harness this energy? Again, what's in the form of X-rays?
If we could build a black hole garbage disposal, that would be the most fantastic source of energy we could have, because we get rid of all the garbage, throwing it down the black hole, and it would produce enormous amounts of energy. I don't see this as being feasible in the short term. It could be that we know so little about black holes that it could be that we can find, capture, make small black holes. That would be really very nice. Okay? That's it, I think. Right.
So now I would like to invite Dr. Vippan to pass a vote of thanks and make a presentation to Professor Giacconi.
Professor Giacconi, I'd like to, on behalf of the audience, I'd like to thank you very much. I was expecting some of the students to come here to sleep, but I noticed none of them. So I think they would go home to start thinking how to build a little black hole garbage. But I think we don't have to look far, because in every class when I look at the student, I find many black holes because they go through them. So I think you have stirred up really a lot of interest, and I certainly hope that Nobel Prize is not limited to Europe or America. And I hope that some of our students here would give them a lot of what I call expectation. That in the future, maybe among one of us here could be another Nobel laureate and come to give a lecture here at Asian Group. So on behalf of all the audience, I'd like to thank you very much, and shall we give Professor another big clap?